Have you ever kind of stopped and noticed that there's this hidden language all around us? It's like a secret code written in math, and it's in nature, in art, even in the buildings we walk through every day. Well, today, we're going to decode that language. We're going to see how simple shapes create the most incredible patterns. So let's start with a little riddle. What do a honeycomb, a footprint, and a tiled floor all have in common? I know, at first glance, they seem totally unrelated, right? But stick with me, because by the end of this, you're going to see how they're all speaking the exact same geometric language. They're all part of this beautiful hidden system of rules.
So here's our game plan. First, we'll get to know our basic building blocks, the shapes themselves. Then, we'll see what happens when those shapes start to move around. After that, we'll see how that movement creates amazing patterns and how those patterns can perfectly cover a surface. And finally, we'll talk about where you can spot all this stuff out in the real world.
All right, first things first. Before we can jump into all the cool, complex patterns, we really need to understand our main characters here, the simple shapes.
The star of our show is the polygon. Now that's just a fancy word for a simple idea, any flat, closed shape that's made up of straight lines. So triangles, squares, hexagons, you get the idea. No curves allowed in this club. This is the fundamental piece we're going to be playing with.
So how do you tell one polygon from another? Well, you look at its properties. It's kind of like recognizing a friend, you know? You look for their unique features. For a shape, that means asking, how many sides does it have? Are those sides equal? What are the angles inside? These things are basically its DNA.
Okay, so we've got our shapes, but on their own, they're just kind of sitting there. Things get way more interesting when we give them the ability to move.
Now, here's a key word for you, isometry. I know, it sounds a little intimidating, but all it means is that the shape moves without changing. It doesn't get stretched or shrunk or bent in any way. It stays perfectly rigid. The shape you start with is the exact same shape you end with, it's just in a new spot.
The first two moves are super intuitive. You've got translation, which is just a simple slide. Imagine sliding a chess piece across the board. It doesn't flip, it doesn't turn, it just slides. Then you've got rotation, which is a turn around a fixed point. Think about the hands on a clock, just spinning around the center.
Next up, we've got reflection, which is basically a flip. Think about a butterfly's wings. One side is a perfect mirror image of the other. And then there's the really cool one, the glide reflection. It's a neat little two-step move. You slide the shape, and then you flip it. And once you know what to look for, you see these moves everywhere. A row of bricks in a wall? That's just pure translation, one after another. A clock is obviously rotation. A butterfly? Reflection. And those footprints in the sand? That's a perfect glide reflection. You take a step, that's the slide, and then your body mirrors itself from left foot to right foot. That's the flip. See? It's everywhere.
Okay, so we have our shapes, we have our moves, now let's put it all together. This, my friends, is where the magic really starts to happen. This is where simple repetition creates the most breathtaking complexity.
And here it is. This is the big secret, the main takeaway of this whole thing. A beautiful, complex pattern isn't some random accident. It's just a simple shape following a simple rule of movement repeated over and over and over again. That's it. That's the whole game.
The rules that make these patterns work are called symmetries. So a pattern might have translational symmetry, where it just slides and repeats. Or it could have rotational symmetry, where it spins around a point. Or reflectional symmetry, where one half is a perfect mirror image of the other.
Now, these symmetries create two main types of patterns. You have frieze patterns, which only repeat in one direction. Think of one of those decorative borders you see on a wall. But then you have wallpaper patterns, and these bad boys repeat in two directions, up, down, left, right, covering an entire surface, theoretically forever. This brings us to the ultimate expression of patterns, tiling. The official name is tessellation, and it's basically the art of fitting shapes together absolutely perfectly.
The idea is simple, but the rules are super strict. To make a tessellation, you have to cover a flat surface with your shapes, but, and this is key, there can be absolutely no gaps between them and absolutely no overlaps. Everything has to fit together like a perfect, seamless puzzle.
So this leads to a really good question. If you look at a tiled bathroom floor, you see tons of squares, right? Maybe some hexagons. But you never ever see a floor tiled perfectly with regular pentagons. Why is that? Well, it's not just a design choice. There's a very specific mathematical reason.
And here's the secret sauce. Wherever the corners of your tiles meet up at a single point,
all their angles have to add up to a perfect 360 degrees. A full circle. No more, no less. If it's less, you're going to have a gap. If it's more, the tiles are going to start overlapping. It has to be exactly 360. And when you look at the math, it all makes perfect sense. An equilateral triangle has 60-degree angles. 6 of them together? That's 6 times 60, which is 360. A square has 90-degree angles. 4 of them? 4 times 90 is 360 again. A hexagon has 120-degree angles. 3 of them? You guessed it, 3 times 120 is 360. But a pentagon? Its angles are 108 degrees, and you just can't multiply 108 by a whole number to get exactly 360. That's it. That's why it fails.
And what's really cool is you can use these rules to make your own wild-looking tiles. There's a famous method where you start with a shape you already know works, like a square. You just cut a curvy piece from one side and then translate it to the opposite side and tape it on. This new, funky shape will now tessellate perfectly, because what you took away from one side fits exactly into the other.
Okay, let's bring this all home. We've got the shapes, we've got the moves, and we've got the patterns. You are now officially equipped to go out and see this hidden geometric code for yourself.
Just look at nature. It turns out the hexagon is the most efficient shape for tiling a surface, which is exactly why bees build their honeycombs that way. It's the same structure you can see on the skin of a snake or the surface of a pineapple. Nature is an absolute master of geometric efficiency.
And of course, we humans have been using these rules for centuries. The artist M.C. Escher was a genius when it came to creating these mind-bending tessellations. But you also see it in ancient mosaics, incredible Islamic art, and even something as basic as a brick wall, which is really just a repeating pattern of translated rectangles.
So, look around you. It turns out you're literally living inside a masterpiece of geometry. The big takeaway here is that this mathematical language isn't just trapped in textbooks. It's everywhere, in nature, in art, in everything. So next time you see a tiled floor, or a honeycomb, or a brick wall, just remember the elegant, simple system of shapes and moves that's at play. Now that you know the language, what new patterns will you see?